All right, so let's, we're going to continue looking at exponential. I think today we're going to get into a few different kinds of word problems. There's some formulas from, like, if you're familiar, like if you have a savings account and you put money in the bank, there's a formula that banks use. We're going to take a look at kind of a simpler version of the real formula, having to do with what's called interest. We're also going to look at just like a lot of things with population. So if we have like, let's say we started with like some, I don't know, bacteria. And we say, well, the number of bacteria is going to double every day. So we started with 1 bacteria. Tomorrow we're going to have 2. The next day we're going to have 4. It gets really, really big really quick. So we can come up with like a formula to predict, all right, how about like a week from now, how many bacteria would we have? Or a month from now? And then we could ask questions like, all right, how long before we hit 2 million bacteria? Because then once we hit 2 million, you know, something bad happens. So we can figure out some formulas to do some of that.
Guys, tomorrow we'll start getting into like kind of like what we did yesterday. Like look at the chart, write a rule, then graph, and then do comparisons. We'll do the same thing tomorrow, but instead of the numbers getting bigger, right, going from like fractions to whole numbers, what we'll do tomorrow is we'll start from whole numbers and go to fractions. The numbers will get smaller. So it'll be smaller than like decay. Like the same like things we did yesterday, just the numbers getting smaller. And then on Thursday we'll do word problems like this, but again it'll be exponential decay.
So I gave you guys a couple examples of exponential growth. Does anyone know where you would have exponential decay? Like a popular example is like taking half of something and then half and then half and then keep taking half of it. Does anyone know what that's called? You keep taking half of something. Think about like nuclear energy. No. Okay, we'll hold on. All right, so what's the formula to represent an exponential function? What's the formula look like? We got the one for a line, that's the y equals mx plus b. That's one of them. But what's the one look like for exponential? We did in the warm-up. Y equals ab to the x. Which two things do you have to find there? You got to find a and b.
Now, if we guys on that one, right? Take it a little bit. Don't cover the answer in the next one.
Oh.
For the A and the B, right? Like yesterday, if we gave you like a chart, like XY chart, a bunch of X's listed across the top, a bunch of Y's listed across the bottom, right? And we said write a rule. How do we do that using the A and B? How do we figure out what A is? Yep, when x equals 0, look below it, that's your A, right? How about B? How do we figure out what B is? Anybody remember by raising their hand? How do we figure out what B is? So remember, with linear functions, right, we add each time. Nicole?
Whatever you multiply by the y's.
Yeah, whatever the y's are being multiplied by. So that's one way we can look at exponentials, right? We can give you a chart, the XY chart, and say write a rule. A, whatever you find what x is, if x is 0, whatever y is, that's your A, and your B is what it's multiplied by each time. On your reference sheet, there'll be space to write that down too.
Okay, so you guys I want to see if we can make a connection here. We just said that A is whatever value you get for y, whatever that comes out to, when x is 0. What is that point if you graph that point? It has a special name. Does anyone remember what that's called? The what? Not a 0.
Because think about it, if you were going to graph it, right, you'd be at 0, then you'd go up. You'd be at 0, then you just go up.
Yeah? Exactly. Very good. That's your y-intercept. So basically, whatever your y-intercept is, that's your a value. It's where it crosses the y-axis. Good. So from the warm-up, we're going to compare y equals 4 times 5 to the x and y equals 5 to the x.
And I know some people that were with me this morning, you had a hard time with this. But look you got two things that are the same, the 5 to the x. There's only one thing that's different.
So how would you write the answer to that? Compare the two graphs. Told you guys exactly what to write. Yeah? Yeah.
Vertical stretch by a factor of 4.
One more time?
Vertical stretch by a factor of 4.
Yep, vertical stretch by a factor of 4.
So the two things you're comparing, the 5 to the x is the same, right? The one number that's different, the 4, that's what it's getting stretched by. It's getting pulled apart. It's getting wider.
Taller.
Taller.
Okay, and note the spelling of vertical. No E at the end of vertical. Alright, so vertical stretch by a factor of 4. Now, this one, very, very similar, except you've got the negative. Somebody tell me, what does that negative cause to do? Yep.
Maybe like reflect over the.
Yes, reflect, or what's another word if somebody didn't understand the word reflect? Flip it. Yep. So you still have got the vertical stretch by a factor of 4, and it's reflected over the
Yeah, so the
x-axis.
big thing is you don't want to say a vertical stretch by a factor of negative 4. You always want to keep it. You always want to keep it positive.
All right. So now, what would happen if you had a number in front? Let's say a was between 0 and 1. Right? We know when it was bigger than 1, like 2, 3. We just did 4. It's stretched. Well, if it's between 0 and 1, it's going to compress. So let's look at this. Let's say that's your graph. Okay. Here's the height of it. Right there. You just marked it where the box started and stopped. Okay. I'm going to put a line where I think half is. About like that. So I'm going to take and draw a line that looks like to me, it looks like it's about half. So now what I'm going to do is I'm going to take that box and I'm going to make it half as tall. Okay, let's watch what happens. So I'm going to put the box right here. I'm going to put a dot right here so I remember how wide my box was because I don't want to change the width. So I'm going to try to keep it lined up with that dot, but I'm going to make it half as tall. What happened to the steepness of the curve when I compressed it and made it half as tall? What do you mean it got smaller? It's not as steep. So when you compress it, it's kind of like you're flattening it out, right? Think about like it getting squished down. It flattens out, all right? So that's what we just did. There's your original. And that's what it looks like when I compress it, right? So anytime you put a number in front between 0 and 1, it will compress. What do you think would compress more? 1/2 or 1/5? Which fraction do you think would compress it more? Well, think about if I go back to this picture. This one was half as tall. If I make it 1/5 as tall, it's going to compress even more, right? 1/5 as tall might be like that. Now it's being compressed so much you can't even really tell that it's curved. I mean, there's a little bit of a curve, but not as much as there was before. Okay? So the closer your fraction gets to 0, the more and more and more you squish it. Okay, so there's two ways to describe this, not quite like that. So, all right, let me show you the two ways how you can write this. So you can either say that the graph is stretched by a factor of a. So I guess we can leave that, and we could probably just change one word. The graph is stretched. Stretched vertically by a factor of a. That's probably the simplest way to say it, because the other way you could say it is like if I stretch something by a half, that's the same as compressing it by a factor of 2. If I stretch by a third, that really compresses it by 3. So I think we'll say it that way.
Yeah.
So if you stretch by a fraction, just keep in mind it really compresses. Kind of like when you multiply. If you some people think multiply, right? Like rabbits multiply means there's more and more and more of them, right? People think multiply means you always have more. But what if you take a number and multiply by a fraction? Like take the number 10 and multiply by a half. What do you get? You actually just got less. So you multiplied, and a lot of people think, oh, multiply means more. Not always. If you multiply by a fraction, it's actually less. If you stretch by a fraction, it's actually less. It actually compresses. Okay.
Okay, just like yesterday when we said like if A was 4, the wording is going to be exactly the same. You're going to write it the same exact way as those ones we just did. Right? Vertical. The graph is stretched vertically by a factor of 1/2, or 2, or 5, whatever.
And what would that really mean? If it's stretched vertically by a factor of 1/2,
It's getting smaller.
it's actually getting squished, yep. Because you're stretching it by a half, so it's really squishing. Now, what happened when A was negative yesterday?
It went up and left. The graph.
If we had to describe it. Yeah, we gave
Oh, it's reflected over the x-axis?
Yeah, and that stays the same.
Yeah.
So, if you put like a negative 1/2 in front, the negative does the same thing, even if it's a fraction.
If we were going to compare that, the wording would be exactly the same. The graph is stretched vertically by a factor of 1/2, reflected over the x-axis. If it's negative, we never want to say it's reflected by a negative number. Well, it's stretched. We never want to say it's stretched by a negative number. By saying it's reflected, that takes care of the negative part.
Yeah, if you guys write on the test stretched vertically by a factor of negative 1/2, that's not gonna get marked right. Right? If it was negative 1/2, you'd say what Mr. Roy just said, and what's written right here. It would just put in 1/2 or whatever.
Yeah. There's no when we're asking you to compare graphs. There's no when it's negative, you have to add that. When the number is negative, you have to add that extra piece, reflected over the x-axis. So it's actually being transformed twice. It's getting stretched and it's getting reflected.
Okay. So any question on that? Anyone need to see like a visual? I think we have. We're gonna sketch one by hand.
It wasn't done writing.
Okay, well, while you're copying that, I'll show you something. Let's see, I should have enough room.
Alright, I'm done writing.
Alright, so let me graph 3 to the x. Somebody tell me a number I could put in front of that to compress it.
-2.
That would stretch it.
A fraction.
Yes, I need a fraction.
1/2.
1/2. So 1/2 3 to the x.
What about -1/2?
We can do that one after.
That's what we need.
So here's the original.
Here.
Now remember, the one in red is going to look compressed, so it's going to curve up later. It's going to be a little bit squished. See, it's not quite as steep. It's only 1/2. Now, if I put in something like, let's put in 1/5, that's going to compress it even more. Okay, that's going to squish it down 5 times as much. So watch the one in black. See how the curve in black is even less steep than the one in blue and the one in red? Now, somebody said, let's throw a negative in. Let's take the red one and make it negative. What's the negative do? It does what? It flips it. So watch the pink one. Instead of curving up, it's going to curve down. It's been flipped. I think it was the red one flipped. Maybe it was, yeah, it was the red one flipped.
Imagine.
Okay. All right. So let's write some of these out. All right. So this right here, this is what you're comparing everything to.
No, 3 times 2 to the x. Because that for A says 3 times 2 to the x. No,
That was 32.
3 times 2 to the x.
That needs to be more bold next time.
Okay,
Or both?
yeah, it's the same. No trouble. Overlap.
So, 3 times 2 to the x. Okay, look at right here. 2 to the x, 2 to the x. That has to be the same to do this kind of problem. Right? So, compare the graph of the function. So when you see the word compare, that's where you're writing out that sentence we keep telling you. Right? So how does example A compare to what I circled? Tell me what it...
What's that 3 gonna cause example A to compare to y equals 2 to the x?
I would say
Keep going.
by a factor of 3.
There you go.
Yeah. So I'm just going to write...
Remember,
We only add the by the x-axis.
yeah. And like we said, whether it's a negative, whether A, the number before, the thing that's the same, in this case 2 to the x, that number before it is a whole, we're gonna write it the same way no matter what. It's always gonna be a vertical stretch. We just want you to understand that if it's a fraction, it is getting kind of compressed. We don't have to write that, but it is getting compressed. We just want you to understand that.
Hold on. Okay, yeah.
Oh yeah.
Right, so I just said example A, that one's a vertical stretch by a factor of 3. How about example B? Yeah?
Vertical stretch by a factor of 3 reflected over the x-axis.
Yeah. So I'm just going to paste what I already have there. It's a vertical stretch by a factor of 3. And Donovan said one other thing, reflected over the x-axis. How did he know that? What was there that told him that? Yeah, the negative right there. And reflected, again, if you don't like the word reflected, you can just say flipped. Reflected over the x-axis. Okay, pretty much in math, anytime you put a negative in a function, whether it's inside the function or outside the function, it causes something to flip. Sometimes it flips up and down, sometimes it flips left and right. But negatives usually cause things to flip. Okay. We're not, I don't think we're going to look at it, but if you put the negative over here instead, that would cause a flip, but it wouldn't be over the x-axis. If you put a negative up here, it would be the y-axis. All right, how about example C? And actually this should say B. Example C.
Would we ever have a horizontal stretch?
Well, that's, if you put it, you could, yes. If you did something like this. Instead of multiplying by a number in front, like 2 times x, let's say you did something like, just make a simple one, like that. That would be horizontal. Because instead of putting the 2 here, 2 times 3 to the x, you put the 2 up here. That would cause horizontal. Yep. We don't really get into that in this class too much at all. How about this one? Y equals 1/3 times 2 to the x. Yep. Example C is a vertical.
But just remember that graph is getting pushed down. It's getting shrunk. It's not going to be as steep.
It's kind of like said, oh, I'm going to take the amount of money that you make per hour, and I'm going to multiply it by 1/3. Is that a good thing? No. Again, most people think, oh, look at multiply. Multiply means more and more. Not if I multiply by 1/3. If I multiply your salary by 1/3, it just got smaller. It didn't get bigger. So same thing here. Mr. Roy just said it's actually getting compressed smaller. Okay? But it's fine to say it that way. We're saying it this way just to keep it in line with what we did yesterday. So you can write the same sentence every time. All right, how about this one? Example D. Yep, Winnie?
Vertical stretch by a factor of -1.
Nope, not quite. Example D is a vertical stretch by how much? 1/3. That's all I see there. It's a vertical stretch by a factor of 1/3.
So you don't take care of the negative?
How do you take care of the negative? That's a separate
Oh, you
sentence.
reflect it.
Yes, and reflected over x-axis. So remember, if you see that negative, you've got to write a whole separate sentence at the end. Okay? Questions on that? All right.
I didn't. No.
Okay, so next one we're going to do is a word problem. Okay, we're going to take a look at how to do this one. It says Noah has 5 butterflies. Okay.
That's pretty odd.
Yeah, about 5. Every year, the number of butterflies triples.
Okay. Order.
Write an exponential function where y represents years and b is the number of butterflies. All right. What do exponential functions look like as a formula? We've got a.
X plus B.
That's lines. Y equals ab to the x.
Oh, of course.
Now, think about what the a and the b mean. What is the b? How do you figure that one out?
We give you a table.
It's what? It's what you multiply by. It's what you're increasing by every time. In this case, it's every year, right? So this is what y is multiplied by. Now a. Or b. Whatever. A. Yeah, A. A is when x equals 0. So it's the value of y when x equals 0. Okay, so what I think I'm going to do is I want to do this, but I think I'm going to change the letters around. Okay, because it's going to be
Why? It's gonna be funky.
y. Because those are not a good way to have those letters. We're going to get a little confused. So let's let, we're writing an equation for the number of butterflies. Let's let y be the number of butterflies, and let's let x represent the number of years. If you do it that way, it's going to fit more in line with the formula. If you don't want to do it that way, we can use the letters the way they were, but you're not going to like it. It's going to be confusing. All right. So x is the number of years. Y is the number of butterflies. All right. Let's see if we can figure out A and B. And the other problem is we already have a B. We already have a lowercase b in our formula. I think it's going to be confusing if I put a capital B and a lowercase b in the same formula. You're going to be like, why are there 2 b's?
Yeah.
One's capital, one's lowercase. It's going to be weird.
We can do caterpillars.
We could do caterpillars next, yes. Sure. So let's figure out. B is going to be the easy one. What are we going to multiply by every year? The number of butterflies, what's happening to it? Okay. What are you multiplying by each year? Yeah?
3.
3. So that's how the number of butterflies is increasing. What do you multiply by each time? 3. Okay, there's B. So now we got to figure out A. A is the value of butterflies when x is 0. What does x represent in this equation?
Years.
Years. So what does that mean if x is, like if x is 2, that means after 2 years. If x is 5, it means after 5 years. If x is 0,
It means that he hasn't bought the butterfly.
it means after 0, it's like right, so what does that mean? If we're
Like
after,
right when he bought it.
it's like right at the beginning.
Yeah,
Right?
Yeah, so it's fine.
He has 5, exactly.
Oh, they're just chilling in his house.
So after 0 years have gone by, that's the beginning. That's the initial amount. So that's how another way you can think of A. It's the amount you start with, right? So he started with 5, and it's going to triple. That's all you have to do. Now just fill in A and B, and there's your formula. So what's going to be my formula for the number of butterflies?
Y equals 5 times 3.
5 times 3 to the x.
Yeah. That's a lot of times, guys, you just gotta pay attention to what directions asked, because we may not ask you to solve it, we may just say, write an exponential function. That way, if we could give you any number of years, and you'd be, based on that function, you'd be able to tell us how many butterflies he has after 10 years, 20 years, 3 years. But in terms of setting that up, that's all you have to do, you don't have to solve.
So let's try that formula and see if it works. The number of butterflies is tripling every year, right? So let's figure out after 5 years how many butterflies. Right, let's do 4 because that's a little easier to do. 4 years. So from year 1 to year 2, what happens to the number of butterflies? Triples. Year 2 to year 3. Triples. Year 3 to year 4. Triples. So to get to year 4, it's going to triple 3 times. Right? So let's see what happens. 5. Triple it once. That's year 2. Triple it again. That's year 3. Triple it again. That's year 4. All right?
Sorry, Dad. Eat them.
Now, that wasn't that bad to do because I only had to triple it 3 times. Right? If I had to do that to say like 30 years from now, how many? That's going to take way too long. That's where the formula comes in handy. But let's check and see if the formula works. So this is how many butterflies he's going to have after how many years? 4. Let's plug in 4 for x and see what happens. Okay, remember the number 135. All right, keep that in mind. 3 raised to the 4th power times 5. Is that what we had?
Nope.
No.
135.
3 raised to the 3rd power times 5. That's what we had? Yeah.
That's better.
I just typed it in.
I'll begin to see.
All right?
Oh, yeah.
So that means it would be 27 years, right?
So that's after, I did after triple. So 2, 3, yeah. So that's how many butterflies he would have. So I got the same answer using the formula as I did using doing it by hand. Now, if you wanted to do it for 30 years, you could do times 3 and, just keep track of how many times you pressed it. But that's going to take forever. Just use the formula. It's a lot faster. Okay. Any questions on that? Alright. It's a little weird because we started with year 0. A lot of times, like when I start with something, I usually start with 1. Like if I was counting how many people in the room, I would go 1, 2, 3, 4. I wouldn't go 0, 1, 2, 3, 4. Then I'd be 1 off. So most of the time when we do exponential equations, that's just how you do it though.
And guys, sometimes,
Start with 0.
Guys, sometimes with something like that, we may give you, in the problem, we may give you the formula. Like y equals 7 times 2 to the x. We might say after how many years, how many, whatever, butterflies do they have after 3 years? Just plug in the number of years into the formula and you'll get your answer. So sometimes you may not even have to set up the formula. You just have to plug in, know that x represents years, plug in the number of years and solve.
So the kind of things that we've been looking at, these formulas that go up very quickly, it's called exponential growth, right? And a lot of people don't realize how quickly something goes up when it's exponential. Okay? And there's a pretty kind of common thing. Like, would you rather me give you a penny right now, and I say I'll double it every day for a month? Or would you rather me just give you like $30,000 today?
$30,000 today.
Today? All right, let's see what happens if I start you off.
I'd rather get the penny.
I don't know.
Start you off with a penny and then double it every day for 31 days.
That's a
Right?
lot.
Right? Watch what happens. So after tomorrow, all right, you only get 2 cents. So it's 2 days, 3 days, 4 days. Now I'm getting into big money. 5 days, 6 days, 7 days. After 8 days, you're already at the dollar mark. We still got 31 days, right? 9 days, 10, 11, 12, 13, 14, 15. So now at the 15th day, you're already in the hundreds.
Oh.
I would have given you 30,000.
That's a lot of money.
But let's see what happens. Day 16, 17, 18, 19, 20. Day 21, well, actually not yet. Day 22, day 23. I'm already more money. I would have given you 30,000.
Oh.
But it hasn't even been a month yet.
Look at what happened.
24, 25, 26, 27, 28. After 28 days, so even if it's the shortest,
Making millions.
Making millions.
right? Even if it's the shortest month of the year, and I start you off with a penny and double it every day, by the end of February, you're already a millionaire. So it was a lot better to take the penny doubled every day
Yeah, I would take the penny double.
than to take $30,000.
Hey, go to 31.
Go 31. So $10 million.
Oh, 10 million.
30,000, 10 million.
10 million.
10
10 million.
Wow. That's not even enough.
Okay, so guys, what I'm trying to show you is exponential things. Even if you think they start very, very small, they go up really, really fast.
What would you do with $10 million?
I don't know.
So guys, like Mr. Hager said, guys, like yesterday when we had you graph something like on the homework,
You know we're being recorded.
we had you graph something like that, right? Then you had to do like -2. Guys, listen please. -2, -1, 0, 1, 2, right? And it started off really like your first couple points were just above the x-axis. Then the third point, a little bit higher. Then you get to that fourth point, it got quite a bit higher. That's exponential. You start off really, there's not a lot of growth at first, like we saw with the example Mr. Hager just did. You had 2 cents, 4 cents, 8 cents, 16 cents. But after that 6th or 7th time, it really took off. Joe, please pay attention. After that 5th or 6th day, it really took off. That's an exponential. All right? Remember, the values are going up into the graph goes up to the right. We'll deal with stuff tomorrow that goes in the other direction, up to the left. That'll be something different. All right? So if we're giving you, like I just talked about, for something that we just did, we may give you the formula. And we say, okay, we'll say what everything represents, and we'll say X represents years. After 3 years, how many butterflies will Noah have? Plug in 3 for X and solve. Say if the formula was this. I'm just making it up. We give you that formula, and we say X represents years. Just plug in the number of years, and you'll get your answer. We're already giving you the formula. All right? You okay?
Yes.
You mean like a frog or something? Okay. All right. So now, if we're not giving you the formula and we ask you to write one, so yeah, we have y equals a times b to the x. But again, that's more for if we give you like the x and y chart and we ask you to write a rule. Or if we're going to have you graph it. If we're giving you a word problem, you're going to want to use something like this. All right? So what on your notes you have y equals, and you have the parentheses. You just have to write in the a, the 1, the r, and then the t.
So this kind of, so the last one we did was also a word problem.
Yeah.
We did use that y equals
Yeah.
ab to the x. This is a problem where they're going to tell you something is going up by 3% every
Yeah.
year. So you use this one when
For
you have
percentage problems.
percentage problems.
So if you want to add that.
Yep, we have a percent one, I think, coming up.
Yeah.
So the last one about the butterflies, that wasn't a percent problem.
Yeah.
It just said the number of butterflies tripled. There was no
And
percent.
like I said, guys, for something like that, we may, the formula may be like in the problem. We might give it to you in the problem, and you have to just figure out, okay, If it's after 3 years, like I said, plug in 3 for x and solve. Alright? So again, y equals your a, that we talked about before. When x equals 0, what's y, right? Where you start. That's your initial amount. If you deposit $5,000 in a savings account. Alright? That's your initial amount of your investment. 1 is always there. It's always part of the formula. And we're going to see this formula again later in the week when we do exponential decay. But instead of being plus, it'll be minus. Alright? So there's problems we can do a percentage that show growth. There's problems that we do a percentage that show decay. We're working on growth today. Alright? Your R is your growth or your interest rate. Make sure you do it as a decimal. So as we said your interest rate was 3%, it'd be 0.03. I have to plug it in as 0.03. That's why we put in parentheses as a decimal. You've got to make sure you change it. You can't put it in as a whole number 3. You have to change it.
Because that would be like getting $3, not like $3.
So, and like I said, if it's a single digit number, all right, 3, 7, 9. Make sure you put 0, whatever the number is. If it's a double digit number, it's easy. Just put 0.10, 0.30, 0.52. All right, and then the t is going to be the time period. How long? 3 years, 7 years, 8 years, whatever. All right. So the biggest thing with this is you want to make sure that percentage, right? Make sure you make it a decimal. And if it's a single digit number, you're going to put 0.0, whatever the single digit is. If it's a double digit like 11, it's 0.11, right? Everybody good with this? So so what I would do for this one, right? So write it again. Here, write an exponential function. We don't have to solve. We just have to set it up. Donovan?
Our problem's different.
Is it? What is it?
It's $250 in a savings account and 4% annual interest.
Okay. So
Is that the next one?
No, that, ours says example 3 as well.
so what? Let's see.
Yeah, our example 4 has like the average in the school is 10.
Okay. So 250. I'll just change it. So we're saying we'll go 250. What's the percentage, guys?
4.
Okay, 250, 4%. We can change it. No big deal. Same type of problem. We can change it. All right. So first thing I'm going to do, guys, is I'm just going to write out the whole formula. I'm not going to plug anything in. And like I said here, it just says write an exponential function. Right? We don't have to set it up. We don't have to solve it. So y equals a parentheses 1 plus r t. Now, if you want to just go ahead on the test, on homework, you want to go ahead and stop plugging in numbers, that's totally fine. All right? If you don't want to write it out like this. I'm just doing this so you can see how we're going to plug everything in. All right? Yes.
So would it be like y equals 250?
Okay, I like to start. Y equals 250, right?
Yeah.
That's the initial amount, 250. Guys, usually your A, your initial, is the biggest number in the problem. In this case, our biggest number is 250. That's what we start with.
And
Keep
then would
going.
it be parentheses 1 plus 4.04
Yeah,
parentheses t?
yeah. That's it. For this, yeah, we're gonna keep going. We're gonna simplify. Donovan?
Isn't annual like 1 year?
Yeah.
It just be 1.
No, we're gonna leave it as T. We want to make it work. It's a good question, Donovan. We want to make it work for any. We want to make it work for any number of years. I want to be able to plug in however many years I get and solve. All right. But we're not quite done yet. There's one thing on. There's a couple things there we could simplify.
Oh, distributed property.
Well, if there was a variable inside here, we would do the distributive property. All right. But I can just combine what's inside the parentheses. So y equals 250 parentheses 1.04 t. So all I did was, now Donovan, if it was something like this, 250x plus 0.04, then I would distribute. But this is I can combine those two things. All right? So do you want us to simplify this to 250 times 0.104? We must leave it.
No, we can't. You can't multiply 250 times 1.04 because of the exponent.
Yeah.
Order of
So
operation.
so think of it as they're not like terms. Because this has the little exponent of t, we can't do anything with that. This is as far as we can go. So again, we can't simplify anymore because it didn't give us a number of years. Now if it said, okay, I think the next one we'll do it this way, set up the function and then solve for a number of years, we can. But with this we can't.
Oh, good stuff.
So now, for example 4, do you guys have this? Is yours the same or is it different?
10,400, 3%.
Yeah.
We're good with this? Okay. So we can, like I said, we can do this with bank accounts. We can do this with money. All right? We can do it with money and we can do it with populations. Because usually, in most cases, populations increase. Sometimes they decrease. Sometimes, in this case, we're going to say they increase. The population at a school. So write an exponential function to model the situation, then estimate the value of the function after 4 years. So now we're taking it one step further. The last one, the 250, increasing at 4%, all we did was set up the equation, or set up the function. Now we're going to set up the function and then plug in a number of years. So it's a 2-step. Set up the function, it gives me a number of years, plug it in. All right? So for this one, I'm not going to write out the whole, I'm not going to write the whole y equals a, parentheses a, 1 plus r to t. I'm not going to do that. Again, if you fill out the reference sheet, there'll be a space for this on there. There'll be a spot to write that formula on there. All right? So let's see. Our exponential function. So we know we want to start with y equals. In this case, how about Brady? What's my a going to be? 10,400. Remember, whispered that to Brady. Nice job. 10,400. Again, I'm using this formula to set it up. Parentheses, 1, this is part of the formula, plus, Haley, what's my rate going to be? Huh? 0.03, very good. Now, for this, all it asks me to do is set up the formula. I'm not solving yet. So I'm just going to put a little t right there for time. I can simplify. What am I going to simplify to, Yusuf? What's going to be in the parentheses now?
So y equals 10,400.
Yeah.
Parentheses
1 point what? 1.03, right?
Yeah.
Oops. 1.03 t. Again, when we ask you to write it out, when we ask you to write out the function, make sure you simplify what's inside the parentheses. All right? Like we said, we can't do anything with this because it's got the little t. All right? Now, value after 4 years. I'm not going to write my answer yet. I'm going to write my answer here, but I'm going to do my work below it. So I'm going to take this function, right? I can plug in any amount of years and get what my value is going to be. So y equals 10,400, 1.03 t. Now, like Donovan just said, y equals 10,400, 1.03, 4. So it's said after 4 years, I'm just going to change my number of years. Instead of being t, it's giving me a number now. I'm just going to plug in 4. I'm going to say he's going to do it out of, again, something like this, guys, I would suggest doing it on a calculator. But if you put it exactly how it is, it'll come out. So we got $11,705.29.
It's for
That's for the population.
Huh? Oh, I'm sorry. Oops. Let's say it around nearest whole number. Okay, so
It's a lot of people.
sorry, guys. There we go. So it'd be right around 11,705 people.
That's
All right.
a lot of people.
So with that after 4 years, the population of that school went up over 1,000, like 1,300 kids. All right. So again, we took we took the formula that we set up, or the function we set up in the first part, and it gave us a number of years. We just plugged in a number of years and solved. All right? And sometimes, guys, in problems, we may give you the function. We may not ask you to set it up. We may just give it to you. All right? And then you have to just plug in a number of years and you'll solve. All right? Everybody good with that one? All right. Now this one, right? So this is the last thing we got, right? So another type of exponential growth is compound interest. All right? So if you set up like in your bank account, all right? Certain times, depending on how, if it compounds like annually, that means once a year. Semi-annually, twice a year. Quarterly, 4 times a year. Bi-weekly, every other week. All right, there's all different ways that interest can be compounded, right? Right? So this formula is very similar, right, to the one we just talked about. So we're going to get the same thing. We're going to get your initial amount or your investment. That's the same. These things are a little bit different, all right? So your R still stands for growth. You still want to make sure you make it a decimal. 0.03, 0.11, depending. Divided by number of times interest is compounded per year. If it's annually, it's 1 time a year. Semi-annually, twice a year. Quarterly, 4 times a year. You just got to pay attention to what word it's giving you in the problem. I think a lot of times what we do, we're probably gonna have you guys do it like annually. We may have you do one, if it's daily, it's gonna be 365. And sometimes if you, like when Mr. Hager and I were younger, like you get like, you go to the bank, you can open a savings account, and you get like a little book. It's all online now, but you get a little book. And you go there, you get money for your birthday, and you go deposit some of the money, and you'd see, you know, it was, you hadn't been to the bank in 5 or 6 months. You see these little increments of like 5, 6, 7, 8 cents over time. And you get a little extra money in your bank account because you were getting interest. Or if you guys went through online banking, if you look at your savings account, you can see, you know, there's a little bit of a couple bucks every couple months that gets, you know, built up in your account. That's interest. That's the money that bank's kind of paying back to you for having a bank account with them. Works the other way too, like Mr. Hager and I have our mortgages. We have to pay interest to them for them giving us money.
For letting you guys own your house.
Yeah. Right now the bank, my house, the bank owns it. I don't own it. If I didn't pay my mortgage every month, the bank would take the house back. I won't own my house for another like 28 years. I took most mortgages you guys see when you get older, when you guys become seniors. There's a class, a lot of you guys will take it, called financial literacy, and it's all about, I actually co-teach it now with seniors, and it's all about this kind of stuff, like buying houses, savings accounts, banking, that kind of stuff. And then your N and your T, your N still stands for number of times, and then again your T still stands for number of years. All right? So the amount of money A accrued at the end of N years with a certain amount of P is missing. Alright, so I'm not super concerned about these letters A, N, whatever. We can use this formula and we can still, the Y equals one. Alright. So we're just going to change it around a little bit.
You go ahead, Mr. Ray.
Okay. So, guys, I'm just going to go through this one super quick. Again, we can do another one tomorrow too. So Y equals my A. It's always my biggest number, right? I start with 240. Parentheses 1 plus my rate is going to be 9. So it's 0.09 over N number of years.
3.
Annually. How many times a year?
1.
Once. Here, and then NT number of times is going to be 1 times years is 3. All right? I go here, y equals 240. 1 plus 0.09 divided by 1. Anything divided by 1 is going to be itself, right? So 0.09. And then 1 times 3 is going to be 3. Y equals 240. Simplify what's inside the parentheses. 1 plus 0.09 divided by 3. Mr. Hager is going to pump that in the calculator for us. Again, a lot of times, guys, we're going to get, when it's compounded, we're going to give it to you compounded annual, once a year. Again, for something like this, you're going to want to use a calculator. So you're going to get 300, we'll say 310. Oops. 310.81. I'm going to round it up because this is a 6. If I round that up, that'll make that a 1. Make it the next number. All right? That's how that works. And it's just going to take the dollar sign and put it down. And guys, we kind of rushed through that one today, so like Yusuf said, it's a good idea. We'll do another one for a warm-up tomorrow so you guys can see another one. As you're packing up, homework tonight, 6.3, 6.4. By the end of the day, guys, the reference sheet will be up. A lot of formulas this week, so you may want to fill it out. I'm not going to put a lot of examples on there. I'm going to put all the formulas on there that you need. All right? We're going to be after school on Thursday. You have this test, the test on one section next academic week, and then the final exam. So you guys that are close, it's up to you. We'll both be here. Test on Friday, then we have not next academic Friday, the academic Friday after that. That's when your final exam will be. Right? Huh?